talking about is indeed a right and left order domain. This was proved by, I think, Andre and me. Okay. Okay. Now, the next line, third line says, is this domain is semi-hereditary? Again, you will not like that word. Semi-hereditary means what? Whether every projective module, every finitely generated projective is free. That is called semi-hereditary. Okay. You will say, well, did you dream at last night about this question? What does it mean? Why are you saying expecting that? Why are you expecting it to be semi-hereditary? Because it was proved by just now before I said about Zellman, No, and those two guys, that it is proof of domain. They proved for commutative case, it is a proof of domain, which is commutative semi-hereditary means proof of domain. Same thing. Proof is a nice word used by the commutative ring theorists. For the same non-commutative people, semi-hereditary. So commutative semi-hereditary is same as the proof word. So that is why I'm saying we know this result for commutative case that it is semi-hereditary. Is it also true for non-commutative case? We don't know. We are not worked out that. How many time is left, Andre? I don't want to go up for too much. Huh? Yeah, good. Okay, next is, result number 13 is what I already spoke about. If R is a commutative integral domain satisfying IP2, that is every 2 by 2 singular matrix is a product of idempotence, then R is a proof of domain, which is commutative semi-hereditary. Proof domain means every finitely generated ideal is projective ideal is free. Is free. Yeah. Projective is free. Every projective is free. Okay. All right. Next one is let R be a right and left Bezout domain. What is Bezout? Like using the word for just to impress on you that I'm using very difficult. Bezout domains. Bezout domain is nothing. It's a small thing. Bezout domain is just where every finitely generated ideal is principal, like AR plus BR is equal to CR. Any finite, not just two only. A1R plus A2R plus A and R is some CR. So that is called a Bezout domain. Okay, domain means no zero divisors. Domain means no. So Bezout domain means no zero divisors, and it is every finitely generated ideal is principal. That's Bezout. So let R be a left and right Bezout domain. Left means left ideal, right means right ideals. R principal. Okay. Then R satisfies the property IP2. Satisfies IP2 means what? 2 by 2 matrices over R, which singular matrices can be as product of idempotence. So we proved that then R satisfies IP2 this property if and only if it is true for every n, IPn. Yes, 2 is enough. Then if you prove this result for 2 by 2, it is okay for n by n. Only for the Bezout, not for everybody. I'm going to skip things. Okay, number 16. What is number 16? If R is a commutative PID, principal ideal domain, commutative, please, then 2 by 2 singular matrix is a product of idempotence. It's a beautiful result. Applies to integers, for example, and many other situations. So if R is a commutative principal ideal domain, then any 2 by 2 singular matrix is a product of idempotence. Oh, wonderful. Now we talk about another nice thing. Matrices which have only 0 and 1 entries. They exist in the life. If 0, 1 matrices are quite common because when we go into applications. Anyway, so we are asking now, what about those matrices which are 0, 1 matrices only? It says if you have a ring and A is a similar matrix with 0, 1 entries, then it's a product of idempotent matrices. You believe it? Then it is a product of idempotent matrices, 0, 1 matrices. You would say about the idempotent matrices, will they be 0, 1? Answer is not true. We don't know. I don't think we even try to see that. It's not going to be true. They're just idempotent matrices. The entries may not need to be 0, 1 only. I doubt. But they are part of idempotence. Okay, here's a proof, but I'm skipping it. Proof is not difficult, but I'm skipping it. Okay. I hope you know what is a permission matrix is. I mean, most people know, but maybe some not. That is, each row and column has only one non-zero entry. That is permutation matrix. Quasi means same thing, but you have a 0 row or 0 column. 0 column. Only which is not allowed for the permutation matrices. So if you have a quasi permutation, well, permutation matrix is invertible, so I can't even describe them as a part of idempotence. Permutation matrices are invertible, so I cannot even talk about representing them as a part of idempotence. I want to talk about singular matrices. So quasi permutation has meaning. Can you do that? The answer is yes. You can do that. You can do that. That was shown by Leroy and I. Okay. This is an interesting result. On page 10, which is, let me put it up. Okay. This is interesting. Let R be a local ring. You must have forgotten, but I can remind you. Local ring means which has only one maximal ideal. Two-sided. Local ring is one which has unique maximal ideal only. Only one ideal it has. That's called a local ring. There can be right ideals, left ideals. I'm talking about two-sided ideal. Okay. And these rings are localization. When the ring theorists do a localization, they appear a very much. Algebraic geometers use it. Look, this is localization is not an uncommon process, but I'm talking about local ring. That R be a local ring, which means it has a unique maximal ideal. Then every 2 by 2 similar matrix can be expressed as a product of idempotent. It is true for that also. Wait a second, I'm talking wrong. Let R be a local ring such that each right single 2 by matrix. If you can do that, I'm sorry, I take it back. If this is possible, then R must be integral domain. Sorry. If under the conditions that if you have R, a local ring, which has this property that a 2 by 2 singular matrix is a product of idempotence, then R must be in integral domain. Look, your integral domain may be commutative, mine is not. Any integral domain means A times B0 implies A0, B0. That's what my integral domain is. A0, B0. A, B0 implies A0, B0, or B0. A is equal to 0, B equal to 0. So it says that if you have a local ring where this 2 by 2 matrices, which are singular, if you can represent them as a product of idempotent, then this local ring must be an integral domain. That's a nice thing to observe, that if you are working on the local rings, if you want to expect this thing to happen, then believe it, that has to be first integral domain. Okay, now I divert to a very special and important class of rings defined by von Neumann in 30s. For continuous geometry, he studied this thing. Von Neumann, it's now called von Neumann algebras. In 30s, these are von Neumann algebras. What is that? This is your generalized inverse. A is equal to AXA. For every A, there's an X where A is equal to AXA. Generalized inverse. But we're talking about not over a field, talking about a ring. If this property holds for every A, ring is called regular ring. Von Neumann regular ring. And if you say, well, I can even find a unit element where A is equal to A. I'm saying AX is equal to A for some X. Generalized inverse. But if I can find X which is invertible, then it is called a unit regular element. A is called unit regular element. If I can find U is equal to A, we'll use a unit. But in general, if I have A, X is equal to A, then it is just a regular element, von Neumann regular element. Okay. So we will be looking when regular rings have the property that the matrices over that are product of similar matrices. Stupid. Similar matrices over R can be represented as a product of idempotents. Now this is far being easy. And we could not do it. We have not done it. It was done earlier, about 20 years ago or more, by two great people, Hanna, Hanna, and O'Meara, umlaut Meara, O'Meara. They studied this question, and their papers appear in the London Journal of Mathematics and others, a Journal of Algebra, about this question. When can you do singular n by n matrices product of idempotents? One interesting thing is number 21. If R is a regular ring, by regular ring means what? Every element A has an X, AX is equal to A. That's called a regular ring. AX is equal to A. They said if A happens to be nilpotent matrix, elements, he doesn't talk about the matrices. Because you can talk about matrices also, of course. If A is a nilpotent matrix again, I'm stupid. A is a nilpotent element of a regular ring. They showed it is a product of idempotents. It's non-trivial. If A to the power n is 0 for some n, then A is a product of idempotent. You will say, wait a second, if I take A to be invertible, then what? So I must correct myself that A is not invertible. I'm keep on removing the word non-invertible in my speech, but use only thing I'm talking about when my elements which I'm using for product of idempotents are not supposed to be invertible, they're supposed to be singular. They're supposed to have a zero divisor. You will say, why are you needing that? Well, if I want to represent A as a E1, E2, E3 product idempotents, they have to be killed by somebody. Why? E1 is killed on the left side by 1 minus E1. If I E1, E2, E3, multiply on the left by 1 minus E1, what will happen? E1 minus E1 squared times something. But E1 is equal to E1 squared because they're all idempotents. So E1, E2, E3 is killed on the left by 1 minus E1, and on the right it is killed by whom? 1 minus E3. E1, E2, E3 on the right will be killed by 1 minus E3 because E3 minus E3 squared is 0. They're all idempotents. Anyway, so I have to use the word elements which are not which are zero divisors, which are not units. If I use that word, just take it. So what I was saying, if I talk that, yeah, if R is a regular ring, and if A and is zero product of idempotents, all right. Okay. Then the next is if A is product of idempotents, and hence, oh, one more important thing. If A is a product of idempotents, every idempotent is unit regular. You will say, what do you mean by that? I think I defined before a unit regular element. What is that? A is called a unit regular element if AUA is equal to A, more than the von Neumann inverse. Your generalized inverse should be invertible. AUA is equal to A. I say AX equal. If that is the case, that is called unit regular. That element is called unit regular. Strong. And clearly, every idempotent is unit regular. You'll say, why? Every idempotent is unit regular. Why? Because E1 times 1 times E1 is equal to E1. E1 times 1 times E1 is equal to E1 because E1 squared is E1. And the 1 is invertible in between. If the in-between guy is invertible, we call it unit regular element. If AUA is equal to A and U is invertible, I call A is unit regular. So, I repeat that every idempotent is a unit regular element. And it is known, which is non-trivial, that the product of unit regular elements is again unit regular. Product of unit regular element is again unit regular. That's a non-trivial result. So what does it mean? It means if A is nilpotent, that means if A n is 0, step number 1, A is a product of idempotents by the result of omega. Step number 2, every idempotent is unit regular. So which means A is a product of unit regular elements. But the product of unit regular elements is again unit regular. Hence A is unit regular. So every nilpotent element in a regular ring is unit regular. How much time is left? 2 minutes left. So I stop. Okay, then let me go to the last page. Thank you. These stories are on the ring theorist and maybe algebraist. Now, this comes to the attention of Banach algebra people, functional analysis. They start looking matrices over Banach algebras. Can you represent a singular matrix as a product of idempotents when the matrices are over Banach algebras? All right, and we happen to come across in number of papers, but one was very nice. Okay, that was by okay, Banach algebras. This guy, I'm telling you, Zemannek, in the Bulletin of the London Math Society in 1979, studied idempotents in Banach algebras. So that is a good help to see if the matrices over Banach algebras can be represented, singular matrices, not everybody, as a product of idempotents. There are some papers running around. So therefore, this can be of interest to combinatorics, algebraists, ring theorists, functional analysts, and so on. Thank you very much.
Thank you very much, Professor Iclaa. Jean, are there some questions, some remarks, some corrections, some answers?
So I have a particular question maybe, which might deviate from your overall talk, but I'll still ask. So consider C omega space, space of all real continuous functions defined on compact Hausdorff space, omega. So that's an algebra here, and it's not an integral domain, it's a well-known fact.
Yes.
But I am interested actually in subspaces of C omega space, which have the property that for any two functions in the subspace f and g, if the product is zero, then one of them has to be zero. This is a very integral domain property, but I'm not calling it integral domain because I'm not considering subalgebras. So it's just a subspace with this integral domain property. So is there anything known of subspaces like this with this property of C omega space?
I would say no. I will look at the rings of continuous function by Gilman. He might have something like that.
Okay, Gilman.
Gilman, rings of continuous function.
Okay.
I'm not.
Okay, I mean, this is actually motivated nicely, this subspaces. One might think why such a restrictive condition, but in the theory of partial vector spaces, as you can see, any, let's say you take symmetric matrices with co-positive cone, it's a complex object to study, but it is isomorphic to such a subspace, in the order sense as well. So it's
Yes.
interesting object, that's why I was asking if anything is known.
Object, I think I'll see also, but I don't know it at the spot. Maybe Gilman would book not no more can help you something like that.
Okay, thank you so much.
Sure.
Thank you. Other questions? Let's say the figure again.
Thank you.
Thank you, sir, for giving such a motivating and wonderful talk. I also thank Professor Leroy for chairing this session. Also, Professor Leroy gave a nice talk in the morning on pseudo-linear maps. So now I request Professor S.K. Jain to honor Professor Leroy.
Yes.
So please. Yes, sir. Thank you, sir. We shall now begin the invited talk session. So Professor K.C. Sivakumar sir will chair this session. So over to you.
Good afternoon. This is second day, third invited talk session. We have two speakers. Professor Apurva Kare from Indian Institute of Science is the first speaker. Cholesky decomposition of almost all non-positive matrices.
Yeah. No, I just want forward and back. No laser. Okay, so thank you very much to the organizers for inviting me. So, okay, fine. Okay, so I'll talk about, the Cholesky decomposition is something that we have, if you have ever tried to factorize matrices, positive matrices, you might have seen this. So I'll start by telling you something about it, and then we will get to the fact that there are non-positive matrices. In fact, most matrices are not positive definite, and one can try to, well, how does one try to extend this decomposition to non-positive matrices? So this is joint work with my PhD student, former PhD student, Pratik Kumar Vishwakarma. He is now a postdoc in Canada. Okay, so just to start, so if you take a, oops, sorry, there's no clicker, that's right. Okay, so a positive, a real, so all matrices in this talk are going to be definitely Hermitian and most likely real and symmetric as well. So such a matrix is positive definite if you have many different equivalent conditions. The first one is the definition that the quadratic form is U transpose AU is always positive. So if U is a non-zero vector, then U transpose AU is positive as a scalar. If and only if the eigenvalues are all positive. So as it is real and symmetric. So by the spectral theorem, all the eigenvalues are real, not just complex, and now they are actually positive. If and only if you can write this as B transpose B for some invertible matrix. Okay, you can even take that matrix to be symmetric. So anyway, and positive definite itself as well. Anyway, but yeah, 3 and 4 are roughly saying the same thing. That A is actually a Gram matrix of a basis of Rn. And if and only if the last one is called Sylvester's criterion, if you have seen this before, then if you take any set of rows and the same set of columns, you get a principal submatrix. The determinant of that is positive. So this is all if and only. Okay. And there is a sixth condition, which I have not yet put, but I will add it to this page, which is also, which is roughly like 5, but a slightly weaker 5, and that is the condition that we will work with, which is that the leading principal minors are all positive. So this does not go through for what are called positive semi-definite matrices or non-negative definite matrices, but it does go through for positive definite matrices. So the top entry, the top corner is positive. The top 2 by 2, AD minus B square is positive. The top 3 by 3, the top 4 by 4. You just take the top, the leading principal submatrices, the first k rows and the first k columns. Take the square submatrix, take the determinant, that is positive. As long as all those are positive, the entire matrix, all possible principal minors are positive. This is if and only. And so it is the last condition that we will actually try to generalize or weaken. Okay. Okay. So now I think 101 years ago, not 100 years ago, the following fundamental fact was shown. So it is called the Cholesky decomposition after Cholesky, but Cholesky did not publish the paper. It was in somebody called Benoit's publication in 1924, and he attributes it to Cholesky. The following result, that for any positive definite matrix, the characterizations on the last page, there exists a unique lower triangular matrix. There is a unique matrix L with the following properties. It is lower triangular and of course real. All the diagonal entries are positive. Okay? And the matrix A is L times L transpose. This is called the Cholesky decomposition of any positive definite matrix. It is uniquely a lower triangular matrix with positive diagonals times its transpose, which is upper triangular. Okay. Fine. So this is the Cholesky decomposition. Let me say that, so you can therefore there is a bijection between positive definite matrices and lower triangular matrices with positive diagonal entries. Right? So L and A, there's a bijection now. From L to L times L transpose, from A to the decomposition. Right? So this bijection, so therefore I'll take the set of L's and call that as Cholesky space. Okay. So there's Cholesky space on the one hand, it is in bijection with the positive definite cone or positive definite matrices. These are in bijection. It's much more than a bijection. This map is actually much more than a bijection. We will get to that. Okay, so Cholesky decomposition, of course, is widely used in all kinds of places, numerical analysis, statistics, obviously applications, and so on. And
For example, covariance matrices people do want to and do Cholesky decompose and apply to downstream applications. Okay. But notice that, of course, all of this is true for positive definite matrices. Now, this is, of course, not the general case. Most matrices, if you look at them, do not have positive. If you look at symmetric matrices, real symmetric matrices, most matrices don't just have positive eigenvalues. They can have negative eigenvalues as well. So, what about symmetric matrices with negative eigenvalues? I don't need all of the eigenvalues to be negative, maybe some of them, but anyways, just positive eigenvalues is a much more restrictive case. Obviously, other things are more general. So, what is known for such matrices? There is something known. Here is what it is. So, if you take, I'll call them generic. So, for almost all real symmetric matrices, one has something called the LDU decomposition. So, let us then again take the same. So, let us take the same thing here. So, the leading principal minor is strictly positive. This condition here. Instead of strictly positive, I will say non-zero. It can be positive or it can be negative. So, for example, the top corner entry is plus or minus. Let's just take 2 by 2 matrix. Top corner entry A, B, B, D. So A is positive or negative, and AD minus B square is positive or negative. Independently. There are 4 choices. 2 and 2. So that's what we'll do now. So denote by LPMN the cone of real symmetric matrices. So real and symmetric also. But the leading principal minors are non-zero. They can be positive, they can be negative. If they are all positive, you get positive definite. But every other case is also considered here. Okay. For such matrices, there is a decomposition known in the literature. So theorem, every LPM matrix can be decomposed uniquely into LDL transpose. So now the difference is there is a D in between. D is diagonal. But there is a more conceptual difference. Namely, all the information about the diagonals of L goes into D. So D need not have only positive entry. The diagonal matrix D can have negative diagonal entries as well. Otherwise, again, it is a positive definite matrix. So, but now all the information about the diagonals from L is taken into D. So L or L1 and L1 transpose have diagonal entries 1. So that is different in spirit from the Cholesky, where the diagonal entries were allowed to be free, but positive. Here they are all 1, positive but 1, and D can have negative entries as well. So it's a different thing in spirit because of the presence of the diagonal matrix. So now the question is there a generalization of the Cholesky which is similar in spirit to Cholesky? Not to this one. Okay? And which specializes to the Cholesky on positive definite matrices. So we want to have a generalized Cholesky decomposition which recovers the usual Cholesky if your matrix is positive, but it generalizes to more matrices, maybe to these LPM matrices itself. It might be to these guys. And in fact, so the goal of this talk is to tell you that the answer is yes. There is such a generalization. It in fact applies to exactly these matrices, the LPM matrices, but I will factorize them in a different way, which is similar in spirit to Cholesky and not similar to this one. So the diagonal entries, I will give you a LD-L transpose decomposition. The D will have no degrees of freedom. Here the D can have all kinds of real positive and negative entries. The D will have no degrees of freedom in our parallel decomposition. And the diagonal entries of L will be strictly positive, just like the Cholesky.
No zero allowed.
No zeros are allowed, so that's why I will only take non-zero in principle. Okay, so first of all, let's revisit the cone. Let's look at the cone a little bit. So all leading principal minors are non-zero, so which means, as I just said, for 2 by 2 matrices, you have 2 choices. The first one is positive, the top corner is positive, determinant is positive, top corner is positive, that is negative. All the 4 choices. What about in general? Well, there are 2 power n many choices. So first one is plus or minus, the next 2 by 2 is plus or minus, and so on. You can ask, is every such configuration of signs, is every such sign pattern realized? Or maybe something is a vacuous condition. Maybe one of these doesn't happen. So maybe there are only 2 power n minus 1 choices that are actually valid. The answer is all of them are valid. For if you think about it for 2 minutes, you can actually find diagonal matrices with this thing. And diagonal matrices, the choice of diagonal entries is completely independent. So therefore, they are all existing. And I will give you an example of these. So on the next slide, so first of all, given a sign pattern, which is, collect all the signs plus or minus together, Given such a sign pattern, let's call LPM n of epsilon. Epsilon is a tuple of sign pattern, to be all the real symmetric matrices with the leading principal k cross k determinant of sign epsilon k. So it might be plus, minus, some 5 tuple of signs, some sign pattern. So here is an example of a matrix that belongs to this class. So if all the epsilon k's are 1, then that is what is all epsilon k's are 1? It's all real symmetric matrices with all leading principal minors plus. That's positive definite. What about negative definite matrix when all the eigenvalues are negative? Well, that is the negative of a positive definite matrix. So k cross k minor should have minus signs everywhere. So it's minus 1 power k. It is not minus, minus, minus. It is minus, plus, minus, plus, minus. So it's slightly different. It's minus 1 power k. Okay, sorry. So the example is on the next slide, not on this slide. So the proposition then is that this, first of all, this cone is obviously a disjoint union of these 2 power n cones, because the cone itself has a definition that the leading principal minor is non-zero. Now the non-zero can be plus or minus. So there are 2 power n choices. This is a disjoint union of 2 power n subsets. And I keep calling them cones. Cone just means that a subset of matrices is a cone if it's closed under rescaling by positive scalars. If you rescale any matrix by positive scalars, the leading principal minors don't change signs. They just get multiplied by c power k, where c is the scalar and it's positive. So these things are cones. Each of the subsets on the right is a cone. The union is a cone. The only question I was asking is, are those subsets, are those subcones non-empty or not? Fine. The overall cone is open and dense in all symmetric matrices. So as I said, my goal is to give you a factorization that works for all of these things, just like the LDU factorization, but similar in spirit to Cholesky. Now the Cholesky factorization fails on all but one of these cones. The Cholesky factorization only works for positive definite matrices. This is going to work for every one of these. So it works on an open and dense set. Complement of this symmetric matrices as zero Lebesgue measure. So why does the complement have zero measure? The openness is clear because, well, it's an intersection of open condition. The determinant is non-zero. That's open condition. Intersection of finitely many open sets is open. Why is the complement zero Lebesgue? Because again, the complement is a union. It's an intersection of k of n open sets. The complement is a union of n closed sets, but each of those closed sets is what? The determinant k cross k equal to 0. That's a polynomial, that's the zeros of a polynomial. It's a hypersurface of codimension 1. Sorry, it's a hypersurface of, it's for codimension 1, and codimension 1 means Lebesgue measure, full volume, full dimensional Lebesgue measure is 0. Right? So that's why the union of n closed Lebesgue measure 0 sets is Lebesgue measure 0, null set. So this set is really nice. It's a dense set of matrices, it's open, and it has 0 measure complement. Okay, so now for the diagonal matrix, as I said, so every one of these subcones is non-empty because this diagonal matrix sits inside it. I want the 1 cross 1 matrix, 1 cross 1 minor to have sign epsilon 1. So I take the first entry to be epsilon 1. I want the 2 cross 2 to be epsilon 2. So this is epsilon 1. Put that as epsilon 1, epsilon 2. The epsilon 1s cancel because they are plus 1 or minus 1. You get epsilon 2, epsilon 3, epsilon 4. Just take telescoping products, right? So definitely every subcone is non-empty. It contains this very simple diagonal matrix where each epsilon I is plus 1 or minus 1. Very, very simple matrix. And now for the, So for example, now let me show you how I'm going to generalize the Cholesky decomposition. So if epsilon is the plus, 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 meaning the positive definite cone, then then what does the Cholesky say? It is L times L transpose. But what is this matrix in that case? All the epsilons are plus, so this becomes identity matrix. So it is L times this identity matrix times L transpose for the positive definite cone. It's L D1 L transpose. So the natural question then would be, of course, I could now take L times this matrix times L transpose, where L is from the Cholesky space. L says take lower triangular real matrix, positive diagonal entries, times D epsilon, times L transpose. First question, is this actually in LPM of epsilon? So certainly this bit, if I take the top k cross k, its signs are epsilon k. But if I multiply by lower triangular and on post by upper lower triangular transpose, is that still of the same thing? in the same cone. And that is true for the usual Cholesky because the matrix in the middle is identity, so that won't do anything. The answer is yes. So first of all, basically by the Cauchy-Binet formula, you can check that any L from the Cholesky space, positive diagonal is lower triangular real, times d epsilon times L transpose is in fact of the same kind. The top k cross k minor is the sine epsilon k. That doesn't change. So now you can ask, is the converse true? Is every matrix in LPM and epsilon whose leading k cross k minor is sine epsilon k, sine, is it of the form L times d epsilon times L transpose, where L is just from the Cholesky space. And then that would really generalize the Cholesky decomposition to every single epsilon. And the answer is yes again. And somehow we asked a lot of people, but this seems to not have been written down. Everybody knows the LDU decomposition or LDL transpose if the matrix is symmetric, but this particular one seems to be not written down, or at least we could not find it and nobody told us. And so let n be any integer, let epsilon be any sign pattern, and take A to be any matrix from that code. So the leading k cross k minor has size sine epsilon k. Then there is a unique L in Cholesky space such that A equals LD L transpose, LD epsilon L transpose. Okay. So that's the that's the result. That's the first result. That's as I said. Well, maybe your neighbor should. I don't know. He might know more than me. I will ask him actually afterwards. So I mean, so the point is this, right? So you want to do matrix factorizations. So where does one come up with, where does one use Cholesky factorization, for example? So you take covariance matrices or positive definite matrices and you try to Cholesky factorize those. Now, so how do covariance matrices arise as, or positive definite matrices, they arise as gram matrices of vectors in Euclidean space. Nowadays, there is some people are studying data that live on not just Euclidean space but on manifolds or on sometimes on hyperbolic manifolds. And then there is an analog of the inner product which is called the bracket, which is like x. It's like think of like Minkowski space or like this 3+1 space time kind of thing. It's x naught y naught minus summation x k y k. So one positive eigenvalue and n minus one negative eigenvalues, or you can do the other way x1 y1 plus x2 y2 plus x3 y3 minus x naught y naught, where the time coordinate is with negative. So again, so the point is those gram matrices, quote unquote generalized gram matrices, will have negative eigenvalues as well. So then you want to work with, again, you might want to try to factorize gram matrices of that kind. And then now for positive matrices, you have Cholesky factorization. For those matrices with negative eigenvalues, you can try this. So as it is, the study of data living on hyperbolic manifolds itself is quite new. So, but hopefully sometime maybe this might be a factorization people might want to try. But so far it is just completely, for us it was completely theoretical to try and generalize Cholesky decomposition to almost all matrices. And now we can. So it's actually a generalization of Cholesky itself because there is no freedom in the diagonal. Unlike LDU decomposition, in LDU the lower triangular, upper triangular had to have diagonal entries 1. The D was where all the freedom lay. Here there is no freedom in the D. It is one of only a finite set of matrices, only 2 power n many matrices. The entries are all +1 or -1. So there is no freedom inside here. All the freedom in the diagonal entries, just like the Cholesky decomposition, is in the L. So that way it is different in spirit from LDU. It is the same in spirit as Cholesky decomposition. So for every matrix A, there exists a unique L. So again, there is a bijection between Cholesky space, this L, the set of all these lower triangular L's, and matrices with a specific pattern of sign, specific sign pattern for leading principal minors. Not just the positive definite cone, but for every such cone. And the union of all these cones is open and dense in the set of all real symmetric matrices. So there are 2 power n many such cones. The Cholesky decomposition addresses one of them, but now we can address all 2 power n of these cones. So almost all real symmetric matrices can be Cholesky, generalized Cholesky factored. Okay, that means that we have this bijection from the Cholesky space to the LPM cone for every epsilon. L goes to L d epsilon L transpose. And the Cholesky factorization is the fact that the bijection is the inverse map. The inverse map is the factorization. And LDL transpose gives you L, and then d epsilon is fixed. And the usual Cholesky decomposition, as I said, therefore, is when all the epsilons are 1, and it's the inverse map. So phi inverse, it's d1. Okay, so this is fine. This is there. There is a Cholesky decomposition, but not just that. This Cholesky decomposition has this map has very nice properties. So of course, if you take L and you take L goes to LD epsilon L transpose, this is like a quadratic map. It's a squaring. There is some plus minus in between, but it's a quadratic map. The inverse is like a square root map, which might be more trickier. Quadratic map is smooth. It's obviously a polynomial map, so it's very nice. The question is, how does the inverse map look? And you know it's a bijection. So phi epsilon is a smooth bijection because it's quadratic, it's polynomial. Polynomial maps can be differentiated infinitely many times. What about the inverse map? And as the title says, there are other properties that are nice. We will actually say that just like the Cholesky decomposition can be given in algorithm form, so can our generalized Cholesky. So that's the next result. So, but I should point out that this is not always true, right? If you consider this map, this is a polynomial map. It is smooth, it is bijective, it is strictly increasing, but its inverse is not differentiable at x equal to 0. So even if you have smooth bijective increasing or whatever monotone maps, smooth bijective maps, inverses need not be smooth. In this case, fortunately, that is not the case. The Cholesky factorization map, the inverse map, is smooth and it is algorithmic. And I will actually write down some kind of an algorithm later in this, later in the next 7 minutes. Probably. Okay. And moreover, these diffeomorphisms preserve both the map going forward, the quadratic map and the square root map, Cholesky factorization, preserve Borel sets and preserve Lebesgue sets. So preserve those sigma algebras as well, which is nice for measure theory reasons, which I will not have time to talk about today. Okay, so yeah, you can see the preprint for the algorithm. And as a result, we will explore some nice structures. Because these maps are so nice, they transfer some structure on Cholesky space into every single LPM cone, such as the positive definite cone. We will see something about that. So here are some specific, so here are the structures that I want to tell you transfer without any hassle, just because you define the structure on the neutral, on the matrix side to be the structure on the Cholesky side. So this space of Cholesky matrices, lower triangular real matrices with positive diagonal entries. This is a Riemannian manifold. This was worked out not too long ago by Zhenhua Lin in Singapore. And so here is a triangle. It has a tangent space at every point. It's just the set of all lower triangular matrices, not just positive real entries, but all real entries. For tangent vectors, you can write down the Riemannian metric. You can write down the Riemannian distance. I'm just giving you some facts. Right? And as a result of these, because of the fact that this is a smooth diffeomorphism, all these structures transfer naturally to every single LPM cone. So he proved that they transfer to the, I mean, he said, there's nothing to prove. He said that these things transfer to the positive definite cone. So he proved that for positive definite maps, the inverse, the Cholesky factorization is a diffeomorphism. Somehow in the 100 years since Cholesky, but he was the one who proved that the inverse map, the factorization is a diffeomorphism, a smooth diffeomorphism. I don't know why nobody had done this before, but he luckily did. And then we said, well, he has done that for the epsilon equals +1. We can do it for all epsilon. So we did the same thing for all epsilon, and that is proved in the preprint. And as a result, whatever he did, whatever these things that he transferred to the positive definite cone, they transfer to every single cone that we get for free, thanks to his work. But the work here that we have to do is the fact that the inverse of this guy is a smooth diffeomorphism. That we have to do. But then we get these things transferring over for free. And there is also an abelian Lie group structure. So that's a very interesting structure. It's slightly, no. So what is the point? The point is the diagonal, the Cholesky space looks as follows. The strictly lower triangular part are all real numbers. The diagonal part are all positive real numbers. And the upper triangular part are 0. All the entries are 0. So how would you add two things? So well, if you have real numbers, you can just add them. And then the point is not the addition. The point is that you can also do subtraction. If you have positive real numbers, you can subtract, you might get 0 or you might get negative real numbers. You can't, so positive real numbers do not form a group under addition, but they do form a group under multiplication. So you do exactly that. If you want to combine two matrices in Cholesky space, the strictly lower triangular entries, you just add entry by entry, position by position. And the diagonal entries, you multiply position by position. And that's the answer. This is a notation by Zhenhua Lin again. So you add the strictly lower triangular parts, this is what he calls them, and you literally multiply the diagonal parts and you add up these things. So the lower triangular entries are added up in their position, the diagonals are multiplied in their positions, superimposed. That's the answer, and then that has explicit inverse, additive inverse, or inverse group operation. The interesting thing is that this Riemannian metric that I told you, so this Cholesky space is an abelian Lie group under these operations, and this Lie group acts on itself and preserves the Riemannian metric, leaves it by bay. It's a very natural structure that Lin uncovered, and all this structure naturally transfers over to the positive definite cone, and now to every Cholesky, every generalized LPN cone. But now he also showed that this manifold has zero sectional curvature. It looks flat. It doesn't look any kind of curved, positive or negative. So one can obviously ask, how many Riemannian manifolds do you know which are flat? This looks like Iclaa. So is it some exotic thing, or is it just our usual Euclidean space? And because that Euclidean space definitely has a Riemannian metric, it is a flat manifold. So you can ask if this Cholesky space is Euclidean space. And Lin writes in his work that the so-called Cholesky manifold is a Riemannian so in some other paper, is a Riemannian submanifold of Euclidean space, but our Cholesky manifold is not a submanifold of Euclidean space. He wrote that explicitly. And then somehow we were sort of shocked or surprised to see that actually it is Euclidean space. It is not Euclidean space, it actually is Euclidean space. Somehow he missed that fact. But anyway, so I'll skip this part, but I will tell you that one can define this structure here. Actually, I can show you the metric itself, right? Look at this metric here. Doesn't it look like the Euclidean metric? And the answer is it actually is the Euclidean metric. The only thing you have to do is the lower triangular matrices entries are real numbers, keep those as they are. The diagonals are positive, just take the logs. The moment you take the logs, that is also a smooth map, because log from positive to real is a smooth map. Exponential from real to positive is smooth. And then you literally get Euclidean space, and this is the Euclidean metric. So there is no actual difference. This is the Euclidean metric. It is Euclidean space, and somehow Lin missed it, well, but we were lucky enough to see it. So we define an actual vector space isomorphism to Euclidean space, blah, blah, blah. Okay, so the last thing I want to say then, is how big are these cones? So I know that there are 2 power n many cones. One of them is the positive definite cone. One is the negative definite cone. But there are all these other cones in between. Are they of the same size? Or maybe they are different. Maybe the positive definite cone is the largest one and the others are very, very small. They are non-empty. They contain the diagonal matrices. And they all are in bijection with each other because of this Cholesky map, which is a Cholesky factorization. It's a bijection to the Cholesky space from every LPM epsilon cone. So they are all bijectively the same, but maybe the measure is very small. 0, 1 is a measure, uncountable set of measure 1. The real line is an uncountable set of measure infinity. They are in bijection. The volumes are different. So are they the same way? So what we saw is that this is indeed a union of all these guys, disjoint union. Each of these is diffeomorphic to the same set, Cholesky space, lower triangular matrices. So one can of course do change of variables using these transfer maps. Start from positive definite, Cholesky factorize to L, and then take L d epsilon L transpose. So we go from L transpose to L d epsilon L transpose. You can go back and forth. What is the Jacobian of the this map? What is the measure, change in measure that happens? So are the cones equally big? Meaning what is the determinant of the Jacobian of such a map? Go from L to L transpose to L to L d L transpose. Is the modulus 1? If the modulus is 1, then that means it's a measure preserving map. And therefore, if the cone was however big, the other cone is the same size. The question is this modulus 1? The answer is we can actually calculate the Jacobian, and the Jacobian of this map turns out to be another triangular matrix. So this is sort of something that random matrix theorists are interested in, maps between sets of matrices. Now what happens is if you think of a map from Rn to Rn, you get a matrix which is n cross n, which is already large. And the calculating Jacobian and determinant and so on might take some work. What we are doing here is we are going from n square dimensional space to n square dimensional space. PD matrices are dense or open, so this is n square dimensional. So the Jacobian matrix would be n square cross n square, which is huge. N cross n was big, n square cross n square is really big. So that's why it would be, so I was told by a random matrix theorist in my department that, it's of course, the nicest situation is when these matrices are triangular, because then calculating the determinant is very easy. You multiply the diagonal matrix. Luckily, in this case, the Jacobian of any of these guys from Cholesky space to here is triangular, and the determinant of the Jacobian is this. So if you take 2 different sign patterns epsilon and delta, and you compare the determinants, when you take the inverse of one, you have to divide one, basically divide this expression by the other expression of the same kind. The L's and the 2 power n all cancel. The only things that remain are these epsilons for one transfer and epsilon prime or delta for the other transfer. Either way, those things just have modulus 1. So the Jacobian determinant is either plus 1 or minus 1 of the transfer map. And therefore, that is one thing, something very nice. It shows that these cones are equally big. And therefore, I can finally end with some consequences. So firstly, yes, for all n, all cones are equally big, which means that we have extended the Cholesky factorization from the positive definite cone to almost all matrices which are exactly 2 power n times as big. Because each of the other components is exactly as big. There are 2 power n components, so 2 power n times as big. Secondly, these things are all living measure preserving smooth diffeomorphism. So this is a really, really nice map. There are all kinds of nice properties. And so in particular, the Cholesky algorithm that one starts with, if you take any probability density on the full set of LPM matrices, right, which has the same mass on each LPM cone, has the same mass on positive definite matrix, has the same mass on negative definite matrix, has the same mass on every such cone, then the Cholesky algorithm fails with probability. Basically, it only works with probability 1 over 2 power n, fails with the complementary probability. Whereas the generalized Cholesky decomposition I mentioned will work with probability 1. And it is the same kind of, it's an algorithmic map, it's a diffeomorphic map, it's Lebesgue measure preserving, and so this leads to the random matrix theory as well. And I suppose I'm out of time, so let's stop.
That was a typical Apurva talk. 30 minutes by. Any questions?
I have one question about it.
Yes,
So, actually, two questions I asked.
yes.
One is, you said that algorithm will show, you have not shown.
He referred to the archive.
Oh, okay.
I ran out of time, sorry.
You sent me.
But the point is, yeah, the idea is you input a matrix, we recover at the same time the sign pattern and the entries. And the diagonal entries and the upper triangular are 0, lower triangular are this thing. And this, of course, fails if the matrix is in the boundary, but otherwise it will always work. Whereas for positive definite, the moment any of these things is negative, any of the signs is negative, for the usual Cholesky will fail. But the point is, just include this parameter, then the same Cholesky, this is the same algorithm as these guys. So this is a very standard algorithm, you will know, I don't. But this algorithm, basically, I just inserted the epsilons and then it works. But now it works with probability 1, whereas the usual Cholesky would fail with probability 1, large.
Okay, so usually when you do this computation, no?
Yes.
So because it's positive sign, so there is something called pivot growth.
Okay.
Okay, so that numerically creates problem.
Ah.
So in Cholesky, because of positive signs, its growth is always 1.
Okay.
Whereas, for example, you want to calculate usual LU factorization
LU, huh?
or LD, L transpose,
LD.
right? So this pivot can grow and it can be quite large,
Oh, okay.
right? So that numerically creates, problem. Instability it shows. So I don't know what.
Right,
did you
right. So
think about?
yeah, I'm not a numerical analyst, so I have no idea. But yeah, but exactly this kind of question or sensitivity or complexity, all these questions are new. This preprint is 3 months old.
Yeah.
So yeah. So please let me know.
So other one is that see if you just start with LD L transpose.
Yes.
Right.
Yes.
Answer then, for example, this non-zero entries. You can take the absolute value and the sign will be left out.
Okay.
And then you can adjust that square root on both sides.
On both sides, yeah.
And then we'll have in the diagonal plus minus 1.
Yes. Yes.
So from there, is it not possible to deduce this decomposition?
But can one prove uniqueness? Probably one can.
No. I'm saying that deduce. I'm saying that from there, if you take the step, that is the starting point. And then finally, your algorithms.
You're saying so take a matrix which you know, whose signs you know.
Yeah.
And then you decompose uniquely as LDL transpose, and now take away the absolute values on both sides and just leave the plus minus.
Plus minus signs, yeah.
That seems believable, but is it unique and everything? I don't know. So that's
right. So I'm saying that that could be the starting point and see whether it is possible.
That's a good point. Yes, one should see that. Yeah, I should see that. I'll think about it.
Okay.
Just a comment.
Yes.
We studied this question, myself and Larry Snyder, in 1996.
Okay.
There's a paper in Llama
Okay.
we published. We used MATLAB,
Okay.
and we tried to notice the LDU decomposition, because
Yeah.
LDU decomposition.
Yeah.
And we also try to see if you can express as a product of idempotent.
Okay. Yeah.
So that may be interesting to you. You can see in Llama.
Okay.
1996.
I will take it.
Okay.
Thank you.
Okay, so if there are no further questions, let's thank the speaker again.
I request Professor Sivakumar sir to honor Professor Apurva Kare sir. So please.
Another 3 minutes. Welcome back to the last invited talk for today. I have pleasure in inviting Mika Matila from the Tampere University, Finland. Some further applications of the lattice theoretic model in the study of power LCM matrices.
Okay, thank you very much, Professor Sivakumar, for the nice introduction. And also, I would like to thank all the organizers of this conference for this very nice opportunity to present my own results here. It's always nice to be in here in Manipal. All right. So I'm going to talk about my favorite topic, which is the GC and LCM matrices, and also about their, or at least the Hadamard powers of these LCM matrices. And first, I should give you some basic definitions. So how to construct such a LCM or GTD matrix? Well, first of all, we begin by giving this kind of set of positive integers. And we also assume that these elements are distinct. And just for convenience, we also assume that these numbers are listed in this kind of growing order, so that the x1 is the smallest and xn is the largest. And also, in the general case, it's quite difficult to study these matrices. So we have to make some further assumptions about the set. And the assumption that I'm going to make throughout this presentation is that our set S is GCD closed. So if take any two elements of the set S and they take their greatest common divisor, that element should also be an element of the set S. That is the idea. All right, and now we are ready to define the actual matrix. So we have a n times n square matrix, and the aj entry of that matrix is simply the greatest common divisor of the numbers xi and xj. And we use this kind of notation for the matrix. So the LCM matrix, which is going to be the main topic of my talk here today, is defined very similarly, but instead of having the greatest common divisor as the aj entry, now we have the least common multiple.
That case is the set. Those as well.
Yeah, we also keep assuming that just for simplicity. I think soon it will be apparent why do I want to do this. Here are just some very simple examples. So we have the GCD matrix and the LCM matrix of this set of four numbers, 1, 2, 6, 8. And it turns out, although these two matrices seem to be the different sides of the same coin, this GCD matrix is much more pleasant to study, and the LCM matrix is very, very difficult. And also, if you want, we can also study the so-called power GCD and LCM matrices, in which the aj element is simply the some positive real power of the GCD of xi and xj, or the LCM of xi and xj. So you can also think about them as the Hadamard powers of the usual GCD and LCM matrices. That is totally okay as well. So here is some history. So both of these matrix types were originally introduced by HTM's Henry John Stephen Smith already in 1876. So these have been quite for a while out there to study. And if you have heard about the Smith matrix or the Smith normal form, it's the same Smith who invented those as well. Very famous Irish mathematician in his time. Okay, so in the 1990s, the research of these matrix types get some new drive, and these American researchers, Borkel and Lai, conjectured that this GCD closeness would guarantee the invertibility of the LCM matrix, because at the time it was very well known that the GCD matrix is always invertible, and it's also positive definite. But the LCM matrix was not invertible, and even 4 times 4 LCM matrix was found to be possible to be singular. So they wanted to find this kind of criteria that would guarantee the invertibility of the matrix. But that was proven soon wrong by a counterexample. Also another counterexample was given roughly at the same time. And also this kind of solution to the conjecture was provided by Hong, and he proved that up to size 8 times 8, all this condition indeed suffices to guarantee the invertibility. But after that, you can always find LCM matrices on GCD closed sets that are singular. And also another counterexample, like I mentioned, was given. And of course, these matrices haven't been studied very actively after that. And but what we are going to do here is that we take a little different approach, because we have this assumption about the GCD closeness. So we can actually think about this kind of semi-lattice structure that this set S itself constructs. And this is something that the number theoretical approach does not do very well. So this allows us to find a totally new angle to this subject. All right. So here are some more explanation about this. So the GCD matrix is very well studied, but the LCM matrix is very much more difficult to study. And yeah, we keep using this assumption about ZS being GCD closed. And yeah, so in this presentation we apply the lattice theoretic method, and this allows us to prove this so-called Sun's conjecture very elegantly. So I will soon tell you more about what the conjecture is about. But it's not actually a conjecture, hasn't been for a long time. So it was proven by Hong already in 1999 by a number theoretic methods, but here we do it a bit differently. And then we also think about the other question, how about the signs of the eigenvalues? I mean the inertia of the LCM matrix. So what can we say about that in the case when S is GCD closed? But now I would like to start with this kind of factorization, because we need to do this in order to be able to study the matrix. So first we begin with this very simple observation that the product of the GCD and LCM is equal to the product of the numbers xi and xj. And this very simple observation allows us to first factorize this LCM matrix like this. So we have these two matrices on the left and right, and in the middle we have this so-called reciprocal GCD matrix. So what do we do next? We focus on this matrix in the middle, and we apply this Möbius inversion, which is a nice trick. Some people may think that this is a trivial thing. In some sense it is, but maybe the most difficult thing here is this Möbius function that we have over here. So especially if you try to study these matrices in a general case, finding values of this Möbius function is really tricky. But I have good news for you. So in this presentation we will stay with this easy case where all these values are very simple to determine. So at least when we consider the Sun's conjecture. But yeah, so this is something that we have to somehow evaluate and estimate very soon.
So the Möbius function is still plus minus 1 or 0.
Yeah, but it can also have some other values in a semi-lattice. Yeah. So but in this case it only takes those three values.
Depending on the prime factorization between xi and x.
Yeah, actually now the prime factorization
Square free or not.
Yeah, but that is the number theoretic Möbius function. Right. So now we are using the lattice theoretic function, so it's a generalized version of that. So it has a very different kind of features also, but in some sense it's similar. All right, so yeah. So now we attack this matrix in the middle, and we can actually factorize that quite easily because, like I said, we know the theory of the LCM matrices, GCD matrices quite well. So this can be factorized into three parts by using this kind of 0-1 matrices E, which I like to call the incidence matrix, but it is not the incidence matrix that is discussed in graph theory. So this is something a bit different, but still. We get this very nice decomposition. And now when we put everything together, yeah, okay.
What is the partial order?
Okay, so it's I should have put the divisibility signs there. So it is just a divisor relation of very good question. Important question also. So yeah, now we are actually gotten this nice decomposition. And just to point this out, we have been able to express our LCM matrix like this. So it is some matrix times this diagonal matrix lambda times the transpose of the first matrix. So as you probably are very familiar, this is an optimal situation for applying the Sylvester's law of inertia. So this is we can essentially say that the LCM matrix and this lambda matrix have the same inertia. And this is very nice. The only problem is that now we know that the signs of these psi values actually determine completely the inertia of the LCM matrix. So now the only thing that we need to do is find out their signs, or if they can be zero or not. But that can be quite tricky sometimes. And also, if you want to study the poor LCM matrices, then the only difference that you have to do is a slight adjustment to this matrix and this matrix here. So instead of using the this function, you just raise this xj here into the power alpha, and that is the only adjustment that you need, and you get a functional decomposition for those as well. So now it's time to tell you more about the Sun's conjecture. So the story is that in 1997, this professor Guy Sun had this private conversation with Hong, and Hong was studying the invertibility of the LCM matrices at the time, and Professor Sun conjectured that it would be true that if every element of the set S has only or at most two distinct prime divisors, then that would actually suffice to guarantee the invertibility of the LCM matrix. And this conjecture actually turned out to be true, although it took a couple of years for Hong to prove it. But it's interesting that nobody else was knew about this conjecture while Hong was working, so it's also some kind of private conjecture. Yeah. So this is not a conjecture anymore, like I said, and it was proven in 2005 and by a number theoretic methods. And now we take a look at the lattice theoretic solution for this conjecture. And well, I'm not sure how much we need this notation, but there is this kind of number theoretic function denoted by this omega, which simply means that the number of prime divisors of some positive integer. So for example, the omega value of number 12 is equal to 2 because it has only prime divisors 2 and 3, and the omega value of 210 is equal to 4 because it has four prime divisors. Okay, so it turns out that we can do even more than just prove this conjecture via this lattice theoretic means. We can actually, in these situations, give quite nice characterization for the inertia of the LCM matrix as well. So let's do that next. So now we start evaluating the first psi value, which is the smallest element. And this is very simple. The function is simply 1 over x1. And this x1 is a positive integer, so this is clearly positive. No worries. Now, so then we have this kind of situation where, or we could have this kind of situation where this element covers or has exactly one so-called greatest type divisor. Maybe I should actually show you the figure, because essentially what it means that this xi has only two prime divisors. It means that those elements that belong to the set S and divide this element xi has to form this kind of nice sublattice structure. And so it actually can have other types of factors as well, but we don't have to care about them because the Möbius function values of those elements would be equal to 0. So they do not actually affect our function psi in any way. So we can as well leave them out of the picture.
So you're looking at basically the biggest divisors there, and then this is GCD close, so it just
Yes.
forms a nice grid.
Yes, these dots here are the greatest common divisors of these greatest type divisors of xi in the set. That is what I'm doing here.
So the Möbius function is really like a poset Möbius.
Yeah, so here are actually the values of the Möbius function. So if you calculate the value from this element to this element, it's always -1, and same holds for all these greatest type divisors. But if you move on to the second rank, so to speak, then these Möbius function values are always equal to +1. and everything else below here takes the value 0. And that is something that makes our life much more easier. So, but we can of course have a situation where there is only one greatest type divisor, and also in this case, that element takes the Möbius function value -1, so the function psi takes the form 1 over xi minus 1 over xj, and since xj is smaller integer than xj, this means that this difference is negative. So every such element will result as a negative eigenvalue, and the smallest element always produces a positive eigenvalue. Okay, now we need to still consider the situation where the element covers 2 or more elements, and because of this picture that I just showed, the greatest divisors are greatest type divisors are of this type, and we can also arrange them based on the first exponent ai's. And because these elements cannot be comparable, none of them can divide each other, we can deduce from there that these bi's must have an opposite order if ai's have been arranged. So this is certainly nice to have this. And now we use the GCD closeness property, and we know that the greatest common divisor of 2 elements of this type is simply we take the smallest exponent ak, al, well, which in this case is ak, and the smallest of the exponents bk and bl is in this case bl. So that has to be the greatest common divisor. And like I said, we don't have to care about the other elements, possible divisors in S, because they have the Möbius function value 0. In order to explain this more thoroughly, I would have to tell you more about the theory of partially ordered sets. I don't think we should go that way this time, so we will skip that explanation. But yeah, so this is pretty much it, and now we have these pictures like I showed you already. So we are ready to finalize the proof. So here is the psi value in this situation. So there will be this one term that corresponds to the xi itself. Then we have this set of negative terms where the Möbius function value was -1, and we have the set of terms where the Möbius function value is +1. And this looks complicated, but it really isn't, because we simply rearrange these terms, because it turns out that these positive terms are well enough to cancel all these negative terms. So we can actually leave this 1 over xi as it is, and take 2 negative terms together with 1 positive term, that they are related to both, and we can quite easily notice that this term here is positive, and also all the other negative terms we can just pair with some other positive term. So there it is even clearer that this subtraction results as a positive term. So after making this kind of rearrangement, we can notice that every term here is actually positive, and we can conclude that the sign of the psi value in this kind of situation is always strictly positive. And that's it. So that's our proof, essentially. So this is quite nice. And we noticed that never could the psi value be equal to 0. And so that means that the LCM matrix in this case is always invertible. And we also know that there are at least that one positive value, just like there should be, because we have symmetric real matrix with positive entries. So it certainly must have at least one positive eigenvalue. So, but anything else we cannot say based on this. So the rest of the eigenvalues are then negative. And again, it would be possible to study the power LCM matrices as well, at least assuming that the power is at least 1. So between 0 and 1, strange things can happen. And actually, I proved in my PhD thesis that there can be always these zeros. So it is possible to construct such an LCM matrix which is singular for some power alpha, where alpha is between 0 and 1. So it's a very nasty situation. But here we have a very simple example. So I have taken some positive integers satisfying the Sun's assumption of the Sun's conjecture. So all these elements have only 2 prime divisors, or at most 2 prime divisors. I have used primes 2 and 3 simply because we get little smaller numbers, but I could have used any kind of prime numbers here. And here is the Hasse diagram of this situation. And now what we need to do in order to be able to figure out the inertia of this corresponding LCM matrix. Well, we know that this element here produces 1 positive eigenvalue. Then we have these prime powers 3, 9, 2, 4, 8. All of them have exactly 1 greatest divisor. So all of them will result as 1 negative eigenvalue, and all the other elements will produce positive eigenvalues. So just to give you the idea of the matrix, I was not able to fit it on the 1 page, but I think you get the idea from here. So it looks, at least possibly looks like that. And based on that count that I just made, we can notice that there are 5 negative eigenvalues and 7 positive eigenvalues. All right, so that was quite interesting. So what we can do next is we can try to play with this idea a little bit more. So we can utilize this idea of counting or minimizing or maximizing the elements where that have only 1 greatest divisor, and by doing so we are able to either minimize or maximize the number of negative eigenvalues. So let's consider that question next. So it turns out that it is very easy to maximize the number of negative eigenvalues. So if you consider this kind of situation where the set S forms a chain in which these elements are in increasing order, like I said, but here every element xi divides the element xj if I is strictly less than j. So this in the theory of partially ordered sets, these are called chains, and essentially it means that every xi plus 1 is obtained from the previous xi by multiplying it with some positive integer strictly greater than 1. It is also true that in this case the least common multiple of xi and xj is actually simply the maximum of those 2 numbers. So you maybe have noticed the maximum matrices somewhere. So this is a special case where LCM matrices become maximum matrices. And so this what we get in this situation is that this first smallest element will always produce, even if we consider the power LCM matrices, this will always produce a positive eigenvalue because the corresponding psi value is always positive. Then if we consider any other element in this chain, every other element will have 1 greatest type divisor, and the psi value will be the difference of those 2 terms.